As we start the unit, it's first important to go back and look at some information that hopefully we remember from Algebra 1 in order to set the groundwork for dealing with the rest of the unit on systems and their solutions. So the first thing I need to do is define systems of equations and solutions so we're all on the same page. So a system of equations for us is just going to be any set of two or more equations. Primarily, we're going to be dealing with two, but the or more allows us to go into three if we have some time. But again, primarily just two equations is what we're going to deal with. For a solution is going to be a point. We're going to be dealing with points as solutions, and remember, points are always of the form x comma y. So it's going to be a point that makes both equations, remember both here means all, primarily two, but it could be three. So it's a point that makes both equations true whenever you substitute the value in. If we think of it in a more graphical way, whenever we look at solution, it's going to be where two lines intersect. That's if we're looking at a graph. So the next line here, to show that an ordered pair is a solution to a system, and this is algebraically, what I want to do is I'm going to plug the values into the equations. So I'm going to substitute and evaluate. So plug the values into the equations and show that it makes both equations true. It's all about getting true number statements. And a true number statement is something like 3 equals 3. Something like that when I plug it in. So if I go to example 1, the example is dealing with the system of equations. I'm going to deal with the first one as green, and the second one here I'm going to make purple because I can. And the question itself says, show algebraically, so that was plugging values in, and graphically, by putting them on a graph, that this ordered pair right here, 3 comma negative 6, is a solution. So there's no mystery here. It's telling me that it works. It's telling me that it's a solution. So I'm going to prove that this is true. Well, the first thing I'm going to do is I'm actually going to look at it graphically. So if I look at the first line, it's already in slope-intercept form, so there's my b. That's where I begin. Then the negative 7/3 is my m, rise over run. So from there I go down 7 over 3. So it gives me a point right there. Or I could go up 7, and I could go left 3. That would give me another point. I have enough points to get a pretty accurate line. That wasn't bad. If you ever missed, you can go ahead and just make the dot bigger. That's one way to solve that. The second line is going to give me a little more trouble because it's not in slope-intercept. So I have to solve for y. So I'm going to take this 3x over using addition. That would give me negative 63 plus 3x equals 9y. And then I have to isolate the y. So divide by 9 everywhere. And I end up with negative 7 plus 1/3 x equals y. And if I look at that, I can see that I have, again, the b value, my y-intercept, and my slope. Everything I need to graph it. So I'm going to begin at negative 7, go up 1 over 3. That's looking pretty good right there. Down 1, left 3 would be there, and connect the dots. And remember, if I'm looking at it graphically, the solution is where my lines intersect. So I can see right here they intersect at that nice point, and that nice point is 3 comma negative 6, which is what I was trying to find back up here. So I've shown it graphically. That point is on both of those lines, the green line and the purple line. Let's go back and confirm it algebraically. This is a little harder to see. So if I check it in both, that means I have to start with one of them. So I'm going to start with y equals 1 minus 7/3 x. I need to go through and substitute the x and the y value in for x and y. Make sure you get them in the right place. It's easy not to get them mixed up. So the y goes as negative 6, and then 1 minus 7/3 times 3. And just do a little bit of math. On the left-hand side, it's negative 6. On the right-hand side, 7/3 times 3 is 7. So I get negative 6 equals negative 6, which is a smiley face because it's true. So I've shown that that point is on the green line, but I haven't shown that it's actually a solution. It has to be on both. So now I have to check the second line. So I'm going to take the purple as it is, not the slope-intercept form I found, because then I might have messed that up. I want to take the original and just plug things in. Negative 63 stays the same. Negative 3, and then x is 3, plus 9 times, we saw that y is negative 6. So I get negative 63 is negative 9 minus 54. And it's a good thing that when I take negative 9 minus 54, I get negative 63. So that's just proving that it's on the second line. So it's the combination of these two things that helps me say for sure that 3, negative 6 is a solution. If it wasn't on one of the lines, it wouldn't work. So I proved it graphically by showing it intersects, and I proved it algebraically by showing that it works in both equations. If I look at example 2, this one's a little bit different because now in the problem it's giving me an ordered pair again, but it's saying this ordered pair is not a solution. So I need to prove that both algebraically and graphically. So I'm going to use similar colors. And again, I'm going to start out graphically. If it's not a solution graphically, they should not intersect at that point. Now the problem with both of these lines is that neither of them is in slope-intercept. Here, if I just do the algebra, you can go ahead and move the x over with subtraction, and then you can divide everybody by 2. You're going to get y equals negative 1/2 x, and then minus 1. And you can do that algebra on your own, just putting it in slope-intercept. For the second one, it's x equals 2y minus 14. So again, my first step would be moving that over with addition. And I'm going to end up with 1/2 x plus 7 equals y. Those are my two slope-intercept forms. I put them in slope-intercept so it's easier for me to graph. If I go to graph the green, I begin at negative 1, and I'm going to go down 1 over 2. I'm going to do that a couple times because I don't know where these intersect. Up 1, left 2. Count very carefully. Up 1, left 2. Up 1, left 2. Up 1, left 2. And hopefully that should be enough. I'm going to go ahead and put my line down through. Now if we look at it so far, the point negative 4, 1 is right here. So there's a possibility that it could be a solution. It's on the green line, so it must not be on the purple line, because it tells me that it's not a solution. So let's confirm that it's not on the purple line. If I start at 7, I go up 1 over 2, or down 1, left 2. Very carefully, down 1, left 2. Put lots of dots just to make sure I hit it the right place. And it's looking like right up there is my actual solution. So right here, right there, is the solution. But what I'm really concerned with is the fact that it's not the point negative 4, 1. And I showed that because they do not intersect at that point. Now let's go back and look at it algebraically. If I start with the green, x plus 2y equals negative 2, and I substitute my x and my y value, I get negative 4 plus 2 times 1 equals negative 2. So I get negative 4 plus 2 is negative 2. Uh-oh, I get negative 2 is negative 2. But I thought it was not a solution. Well, come back over here and remember, this point, negative 4, 1, right there, is on the green line. And that's what this is telling me. And I'm okay so far because to be a solution, you have to be on both. Now we just have to prove that it's not on the purple. If it's on the purple, we did something very wrong. So let's plug the values in. Negative 4 for the x, 2 times 1 minus 14. So I get negative 4 equals 2 minus 14. This is looking pretty good. So negative 4 equals negative 12, which is not equal to. So I can get a frowny face, or whatever you want to put. The key is I proved that that point is not on the purple line. And if it's not on the purple line, then negative 4, 1 is not a solution. So as soon as I find out that it's not on one of my lines, I can say for sure that it's not a solution. The last thing I need to look at right here is the question, what is the solution to the given system in example 2? So if I look at the solution, remember solution means intersection point. So it's right there. If I hadn't made my dot so big, I could tell that it's right there, which looks like -8, comma, 1, 2, 3. So -8, comma 3 is the solution. And if I plug it in algebraically, it would make both true. So there's a quick introduction and review to what does it mean to be a solution to a system, and how do I show it algebraically, and how do I show it graphically.